Alrighty. Now that we understand what the Gram-Schmidt process is and what it does, right? Let's use it in a few examples. So first, I know this was in just the previous video, but let's remind ourselves of the Gram-Schmidt process here and what we're trying to do. So with the Gram-Schmidt process is we take a collection of linearly independent vectors in Rn, say, okay? So here we have u1 through un. These are our vectors. And what we want to do is the goal here is to find a set of vectors. Let's say wi here, right? Which remember wi, this notation is shorthand for the set of vectors w1 through wn, right? Where I is the index. Sometimes you'll see this notation to be more precise. If you see, I'll write it on the other side here. Sometimes if you shorthand the notation like this, well, if I is understood as the index, then you can just leave it as this. But a lot of the times, if to be more explicit, or if I isn't in the given context isn't immediately understood as the index, what you'll write is you'll write this wi with brackets, and then you'll write I equals 1 in the subscript to n in the superscript. And this just tells you the range of your index, right? Just like we do for a sum, right? When you see like a summation, I goes from 1 to n, same concept. But it's understood in context, so I've kind of just dropped that part for convenience. So what we want then, right, is we want to construct this collection W1 through Wn that's orthonormal, but the span of Wi, the collection Wi, is the same as the span of the collection of Ui's, right? And I briefly talked about why this is important here. It's because if you have, well, if we're looking at a linearly independent set of vectors, and then we're trying to understand the span of that collection, well, then that's a basis, right? Because by definition, those vectors are a linearly independent spanning set. And so what we would be understanding, or what I was saying yesterday is, if you have a basis, let me just erase this whole page here. How do you do that? Cool. If you have a basis for some space, that's your basis, right? That's your notion of length. Like when you're looking at R and you say a basis of R is the span of the vector 1, 0, right? That means you're just looking at the vector 1, 0, and then, well, just all multiples of, so like say you're trying to construct R inside of R2 here, right? Which is why I have a second vector here. So say you're in the XY plane, right? Well, you can construct the whole real numbers, like the x-axis here, just from the vector 1, 0. And then this basis element becomes your unit measurement, right? We would measure, or we would indicate other points on this line being in terms of this vector here, right? And, same for R2 inside of R3 or any subspace, right? These basis elements end up being kind of what you use as like unital, like directions, right? So like we have a notion of how far away something is, right? When we think of R2 as being the span of E1, E2, right? Well, we think about then any point in R2 being like X amount of copies of E1 from the origin. I'll just say 0. And then, something on the y-axis is Y copies of E2 from the origin. Well, I should say y copies of the magnitude, right? Because these are vectors and we're talking about distance. And the magnitude here is 1. And so you want your your unit length in any coordinate direction, you want that to be 1, right? It would be really complicated if we thought of R2 as the span of 32, 0, and then 0, 15, right? Sure, this is linearly independent, and sure, it's orthogonal, but it's not orthonormal, right? And so we have an orthogonal basis for this space now, but that's really inconvenient because, well, in one coordinate direction, you have your units in terms of multiples of 32, but in the other coordinate direction, you have units in terms of multiples of 15, and that's not convenient at all, right? And so what you always want to be able to do is take, and not even necessarily an orthogonal spanning set. You just want to be able to take any spanning set of linearly independent vectors, right? And so basically any basis for a given subspace, and rewrite this basis in terms of orthonormal vectors, so that once you were to try and apply math and do algebra in this subspace, well, the computation would be much easier because your units of your coordinate units are of length 1, right? And so you would have a real notion of a unit in each coordinate direction. So anyway, that's kind of a review of why we care about this. Let's see how we do it, right? So we start with this U1 through UN, and we start by making V1 just U1 here, right? We're constructing, basically what we're doing, the first step is to construct an orthogonal set with the same span. So V1 is U1 here, and then we make V2, we define it to be U2 minus this entire thing here, which if you remember, this is the projection of U2 onto V1, right? And then we do this iteratively or inductively, right? Then the next V3, well, that's U3, and then minus the projection of U3 onto V2. And then you can see here, sorry, minus the projection of U3, or sorry, this should be V1, my apologies, down here. And this should be the projection onto V2, right? And then you just continue this process until you run out of vectors, right? And the last vector is UN, and then minus the projection vectors onto all previous vectors, right? You'll take the projection of UN onto V1 minus projection of UN onto V2 minus projection, blah, 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 all the way up to the n-1 term. And then you've completely exhausted your vectors. And by this construction, by the projection construction here, this necessarily gives you an orthonormal or an orthogonal set with the same basis or same span, right? Then to get an orthonormal set with the same span, well, to guarantee they all have magnitude 1, we just take each of these V1 through Vn, divide by the magnitude, we get what we want, and we have that all of their spans are the same. Okay, so there's a quick reminder of what we do and how we're doing it. Let's see some examples. So let's first just, I guess this is a red example. I'll go with it. Let's consider the following set of vectors. We have 1, 1, 0, 3, 2, 0. You can see right away that these are not orthogonal even, right? But they are linearly independent in R2. So what we need to do now is we need to find W1, W2 with the same span. Right. So how do we do this? Well, we use the Gram-Schmidt process. Let's start with step one. With step one, I'm going to call this first vector U1 and the second one U2, just to be consistent with the notation that I used when I was actually defining or describing this algorithm here. So what's the first step? Well, we need to find V1, V2. And how did we do this? Well, we said V1 is equal to U1, which is the vector 1, 1, 0. And then what was V2? V2 was equal to U2 minus the projection of U2 on to V1, right? And so this might help more in terms of being able to memorize the Gram-Schmidt process, right? Because, I mean, just trying to memorize purely like these symbols can get kind of messy, right? But if you remember first that really at each step you're just subtracting the projection of U in or UI onto all of the previous VIs, then the formula becomes a lot easier, right? So like, for example here, just for the sake of helping memorize, you know, this would be like U3 minus projection, U3 V1 minus projection, U3 V2. And then, so UI, if you would like, is VI minus sum where I goes from, or let's say J, sorry, where J goes from 1 to I minus 1. And then we have, apologies, that was a U, right? UI, J goes from 1 to I minus 1. And then we have the projection of UI onto VJ, right? And so what this would be like, if you wanted to memorize the Gram-Schmidt process in one formula. And then, you know, I guess I should say this is for I between 2 and N, right? Because we don't do it for the first I, we just do it for everything afterwards. So if that helps you with memorizing the Gram-Schmidt process, maybe I wanted to take the time to do that. But anyway, what we have, sorry for my my tangent, but hopefully it was helpful. In this context, right, what is U2? Well, U2, besides a once good band, is 3, 2, 0. So we have 3, 2, 0 minus, and then the projection of U2 onto V1. And this is where then maybe you can just memorize what the projection is doing, right? I'll write it out explicitly first. This is U2 dot V1 over the magnitude of V1 squared times V1. Okay. Then we have 3, 2, 0 minus. Well, remember that the magnitude of a vector squared is its dot product with itself. So if you would like, you could also write this as U2 dot V1 over V1 dot V1, right? Which is, let's see what we have. We have 3, 2, 0 minus, and then U2 is 3, 2, 0 dot V1 was U1, which was 1, 1, 0, and that's over 110 dot 110 times 110. I know this this parenthesis part looks a little overwhelming, but it's really just a number, right? It's a scalar. The dot product's a scalar. The magnitude squared is a scalar, right? So that's all just a scalar. And it looks like we're going to have 320 minus, and then we have, well, let's see, we have the dot product. That's going to be 3 plus 2. That should be 5 divided by, and then we'll have 1 plus 1 is 2, right? So that was the dot product of the top and bottom in the parentheses here. And we're scaling 110 by that. So what we have is 320 minus 5 halves, 0, which gives us the vector. Well, 3 is 6 halves, so that'd be 1/2 and then -1/2 and then 0. And this is our vector v2. And so now we have an orthogonal set given by 110 and 1/2, -1/2, 0, right? You can see that's orthogonal. The dot product is 0. The dot product would be 1/2 minus 1/2, which is 0. Cool. Now, what's step 2? Well, step 2 of the Gram-Schmidt process is to take each of these vectors and scale it by 1 over the magnitude. So let's find the magnitude of V1, right? Well, that's root 1 squared plus 1 squared plus 0 squared, which is root 2. And the magnitude of V2 is going to be root 1/2 squared plus -1/2 squared plus 0 squared, which is root 1/4 plus 1/4, which is root 1/2, which is 1 over root 2, right? Which is, let's just leave it like that. So what we need to do then is we need to say W1 is 1 over root 2 times V1, which was 110, and then W2 is 1 over root 2 times 1/2, -1/2, 0. Okay, so that looks like W1 is going to be 1 over root 2, 1 over root 2, 0. And then W2 is going to be a tax form. Let's see. Well, we have 1 over root 2, which is root 2, right? If you have 1 over A over B, that's equal to B over A, right? And so in this case, we just get root 2. And so W2 is going to be, whoops, root 2 over 2, negative root 2 over 2, and 0. But if you'll notice, 1 over root 2 is equal to 1 times root 2 over root 2 times root 2, which is root 2 over root 4, which is root 2 over 2. So these are actually the same, which means we could rewrite W2 as 1 over root 2, -1 over root 2, 0. And then we have that this collection, well, I'll just say W1, W2 is an orthonormal set with same span as, well, V1 and V2 for sure, because we just scaled V1 and V2 to get these, but also the original U1, U2, right? And what you could do here is, here's a problem. Like this is a problem for you guys. I'm not assigning it for a grade or anything, but I'm assigning it, right? So here's a problem. I want you to show that the span of U1, U2 equals the span of W1, W2, which is R2. So I claim that the span or the subspace generated from the vectors W1, W2 is the XY plane. That's my claim, and I want you to prove it. I'll give you a hint. Think about, or I would say, show that span of W1, W2 is equal to the span of 1, 0, 0, 1, right? Because that's like the standard basis for R2. That's the standard orthonormal basis for R2 that we understand. And so to show this equality, at least, that's my hint, right? See if you can show this by looking at what the projection vector is doing, right? Because there's only one projection vector to look at, and we have explicitly calculated these projection vectors. So maybe see if you can understand the geometry to figure out why, or to convince yourself that these spans are the same, right? Okay. And so what this also does is this gives us, this Gram-Schmidt process gives us a way of finding an orthogonal or an orthonormal basis, right? So I just want to make a remark here. Let's let W be the span of U1 through UN. Let's say this is a subspace of Rn. Well, then the Gram-Schmidt process results in, or let's say the Gram-Schmidt process finds an orthonormal basis for W given by, say, B sub W is W1 through Wn, right? Because they have the same span, they're orthonormal, so they're linearly independent, and so that's a basis, right? And we're starting, I mean, this is a basis too, this U1 through UN, because we've started with the assumption that they're linearly independent, but we want an orthonormal basis, right? And so this gives us a way of finding a more convenient or an easier, quote unquote, nicer basis. Okay, so that's a remark I wanted to make. I want to talk about one other thing very briefly, and then I think that'll wrap up this lecture 15 here. This was getting a little bit long, like just this one lecture, and so I decided to break the fourth video for today, and then I'll post today's video today also, just to kind of try and even out the amount of material that I'm throwing at you per day. But anyway, so let's wrap up this lecture 15 here with looking at orthogonal complements. Okay, well, before we talk about orthogonal complements, let's just talk about set complements. So yeah, first, as I write that second. Okay, so set complements are, let's just give a definition. Let's say we have, let's let A and B, these are two sets. Okay, and let's say with or two sets such that A is a subset of B, right? Well, what does A being a subset of B mean? That means, this means every point, or let's write this mathematically. This is good set theory or logic here, right? What is this A is a subset of B? What does that mean? This means for every element X in A, this implies X is an element of B, right? That's like the logical statement here. That's what it means to be a subset. It means every point in A, if you have a point in A, then it's necessarily a point in B. But what does this also mean? This also means, well, if it's a proper subset, proper meaning, right, you could write B is a subset of B because every point in B is a point in B, right? We don't think of that as a proper subset. A proper subset is one that's not the entire space itself. So for, let's say for A, not B here, right? So we're purely looking at proper subsets. We also have that there exists a Y in B such that Y is not in A, right? This is also what it means. What the complement of a set is it's looking at this collection of points. This is the complement to A in B. So the complement of the set A is going to be all points in B that are not in A, right? Let's draw a picture. Here's the set B, and here's the set A. Say these are subspaces of R2 here. Okay. Then the complement of B or of A in B is everything in B that is not in A. So that's all of these points, right? The notation here is a lot of the times you'll see A complement here. And if it's not understood what its complement, like what's the superset or what A is a subset of, sometimes you'll also see lower script B there to indicate like what it's a complement in, right? This is a complement in B, but sometimes when you're using like ABC, that can be like, there's such a thing as powers of sets, like set A and set C, where like A is raised to the set power C. And so I don't want to confuse here. This is for complement. And another way we denote this is B slash A here. This slash is set minus. Okay, cool. Let's look at an example here. An example would be good. Let's let A be the rational numbers. So if you've never seen the symbol for the rational numbers, it's a Q, like so. Here, maybe I'll just remind us these are called Blackboard font letters. So I'll remind us of the Blackboard font letters here. Z is the integers. Q is the rationals. R is the reals. And then C is complex. If you want just positive integers, then you have the naturals, right? Or whole numbers. So anyway, Q is the rational numbers. What are the rational numbers? Well, the rational numbers are numbers of the form P over Q in R such that P and Q are integers and Q is not 0. This is how you would explicitly write the set of rational numbers, right? Rational numbers are things that can be expressed as a fraction, right? If it can be expressed as a fraction, and whole numbers or integers count as fractions, right? Because it's itself over 1. So this is the rational numbers. Well, then let's let B be the real numbers. Then it's clear that the rational numbers are a subset of the real numbers. But then what's the complement to the rational numbers? What is R minus Q? Well, this is the irrational numbers. Right? This is all real numbers that cannot be written as a fraction because we're taking the complement of those, right? So I don't think we really have a Blackboard font. Maybe some people would use I for the irrational numbers. I'm not sure. But this is irrational numbers. Right? So there's an example of a set complement. Okay. Why this matters, where this came from, is because very quickly I want to talk about the orthogonal complement. The orthogonal complement, well, let's say W in Rn is a subspace. And let's say W is expressed or is generated by W1 through Wn here, right? So W1 through Wn span this, their span makes up this subspace W. Then let's call this a definition here. Well, how about here? Def. The orthogonal complement is, and we write this as W perp. You read it W perp. This is going to be, it's going to be vectors in Rn such that U is orthogonal to the space W. So it's only the vectors not in W. Yeah, I should say here, sorry. Let me be more precise because we want these not to be in Rn or in W, right? So these are vectors U in the complement of W, but it's not all of them. It's not the entire complement, right? It's just the collection of vectors that are orthogonal. So such that U dot Wi equals 0 for all I from 1 to n, right? And so basically it's what W perp is this is a subspace of Rn minus W, right? Because not always, but sometimes when it's proper, there's going to be vectors in the complement to W that are not orthogonal to it, right? And so it won't be, as W perp won't necessarily, and in general, it won't be the entire complement. It's going to be a subset of the complement, right? And it's just, so if you're like looking at a plane here, right, and say, let's say we're in R3. Let's look at a quick example. Say we're in R3 and W is this plane here, right? Well, there are plenty of vectors in R3 that wouldn't be orthogonal to it, right? You can think of a lot of vectors that wouldn't be orthogonal, like vectors that are not in W, right? So the rest of this is R3 minus W. So what W perp would be, it would be the subset spanned by normal vectors, right? It would be the subset spanned by the vector normal to this plane. And clearly that's a pretty small percentage of all vectors in R3 without W. And so that's what the orthogonal complement is. All righty. So I think this is where I'm going to stop for now. And in the next lecture, we're going to get into chapter 5 of the textbook.